Okay, welcome to the deep dive. This is where we take the sources you send our way, unpack the key ideas, and basically help you cut through the noise to get right to what matters.
Yep, think of us as your guides, pointing out the really important stuff.
And today, we're diving into a really fresh academic preprint, just landed. It's called Hyperpruning, efficient search through prune variants of recurrent neural networks leveraging Lyapunov Spectrum. Quite a mouthful.
Yeah. It's by Caleb Zheng and Eli Shlizerman from the University of Washington.
Yeah.
And it really tackles a significant challenge.
Which is?
Getting these powerful, complex neural networks, specifically recurrent neural networks, RNNs, actually working efficiently out in the real world, not just in the lab.
Right, making them practical. Because these RNNs, the ones like LSTMs or RHNs that are so good for, sequences, text, time series, that kind of thing, they can be really demanding.
Exactly. They need a lot of computation, a lot of memory. The paper mentions their computational demands scale linearly with input sequence length and quadratically with network size.
Oof. So longer sequences or bigger networks get expensive fast, especially problematic if you're trying to run them on, say, a phone or some other device with limited horsepower.
Precisely. Which is why people look at things like network pruning.
Pruning, like trimming the fat, making the network sparser.
You got it. Cut out connections, the weights, to make it smaller and faster, hopefully without losing too much performance.
Okay, and how does that usually work?
Well, the traditional way, often called dense to sparse, you start with your big, fully connected network. Then, during or after training, you remove weights, usually the ones that seem least important based on some rule.
And that helps. So.
Yeah, it definitely helps with inference time. Makes the trained network faster when you actually use it. But here's the catch the paper really highlights.
There's always a catch.
The training time. It often remains similar, or in some cases becomes even longer, than just training the original dense network from scratch.
Huh. Okay, so you end up with a faster network to run, but getting there takes just as long, maybe longer. That kind of defeats the purpose if you need to train or fine-tune often.
Exactly. It limits the practical advantage. And that's why newer methods like dynamic sparse training, or DST, came about.
DST, dynamic sparse training, what's different there?
These are sparse-to-sparse methods. So instead of starting dense and cutting down, you start with a sparse network from the get-go.
Okay.
And you try to maintain a constant level of sparsity, a fixed number of active connections all through training. The goal is to speed up both training and inference.
Maintaining sparsity sounds like juggling. How do they do that?
It is a bit of a dance, yeah. You're constantly removing some weights, regrowing others, moving them around, all guided by certain rules, maybe based on weight magnitude or gradients, how much they're helping the learning.
Right. And I bet finding the right rules, the best way to do that dance, is the next hard part.
You nailed it. The paper really emphasizes this. They say there's no universal set of controls for DST that works best for every single network or task.
So finding the best way to prune becomes its own optimization problem, on top of optimizing the network itself.
Precisely. You've got your network hyperparameters, and then this whole other layer of pruning hyperparameters.
Wow.
And this is what the authors formally call hyperpruning. It's the search for the optimal pruning strategy. The methods, the rates, the initialization, all of it.
Hyperpruning? Tuning the tuner. Okay, that makes sense. But like any hyperparameter search, that sounds expensive. How do you know if a set of pruning settings is good without training the whole thing?
That's the core challenge. You run tons of full experiments, but that's slow. The usual shortcut in hyperparameter optimization is to look at early performance. Maybe check the loss after just a few training epochs.
And assume the ones doing well early will win out.
Right. But the paper shows pretty clearly, using their figure 1c, why that's unreliable for hyperpruning.
Okay, looking at figure 1c, it shows two prune networks, pruned 1 and pruned 2. Lower perplexity is better here, and early on, pruned 2 looks way better. Lower perplexity.
Yep. Seems like the obvious early winner if you're just looking at that initial performance.
But then, wow, okay. As training goes on, pruned 1, which started worse, actually overtakes pruned 2 and ends up with lower final perplexity, significantly better.
Exactly. It shows that early loss, or early perplexity in this case, is just not a good predictor of final pruned network performance. It can totally mislead you. You can't confidently throw out candidates based on it.
Okay, so let me recap. We need efficient RNNs. Pruning helps, but traditional methods don't speed up training. DST tries to fix that, but introduces hyperpruning, finding the best pruning strategy. And that search is hard because early performance metrics like loss are unreliable guides.
You got it. And that sets the stage perfectly for the paper's big idea, their core innovation.
Which is?
Using something called the Lyapunov Spectrum, or LS, as a reliable predictor for hyperpruning.
The Lyapunov Spectrum. That sounds mathematical, like from chaos theory or something.
It's exactly from that area, dynamical systems theory. They propose looking at RNNs not just as data processors, but as dynamical systems, systems whose internal state evolves over time.
Okay.
The Lyapunov spectrum essentially measures how the network's internal state reacts to tiny disturbances. Does the state tend to contract, stay stable, or does it expand, potentially chaotically? It's measured by Lyapunov exponents.
So it's like a fundamental measure of the network's internal stability or dynamics as it processes sequences, assuming the input data is sort of statistically consistent.
Pretty much, yeah. They mention it can be applied even with external inputs using random dynamical systems theory. And apparently, some prior work had already hinted that this LS might correlate with trainability or performance.
Interesting. So the LS tells us something deep about the network's behavior. How do they make that useful for finding the best pruned network?
This is the really novel part. They introduce an LS-based distance metric. The core idea is quite elegant. If a pruned network's fundamental dynamics, measured by its LS, look similar to the dynamics of a really good dense network, their reference point, then that pruned network probably has the right underlying structure to learn well, even with fewer parameters.
So dynamic similarity predicts performance potential instead of just looking at current performance.
Exactly. They calculate the LS for the pruned candidate and for a pre-trained dense reference model. To make comparison easier, they project these high-dimensional spectra down into a low-dimensional space like 2D using PCA.
Okay.
And then they just measure the distance, the L2 distance, between the projected points in this LS space. That distance becomes their metric.
And this LS distance works better than early loss.
That's what they show, yeah. Remember figure 1C where early loss was misleading? Well, figures 1A and 1B show the LS story. The LS-based distance, they say, appears to be consistent and indicates that the pruned 1 variant is closer to the dense network for all epochs.
Wait, hang on. So pruned 1 looked worse early on by loss, but ended up better. And its LS distance to the good dense network was smaller than pruned 2's distance, consistently, right from the start.
That's exactly it. The LS distance consistently pointed towards the ultimately better network configuration relative to the dense target throughout training. It provides that stable, reliable, early signal that loss just doesn't have.
Okay, that is cool. You can actually use it to make informed decisions early in the search. It feels like you're measuring something more fundamental.
Right, about the network's capacity to learn, not just its snapshot performance.
How do they calculate this Lyapunov spectrum, though? Is that computationally heavy?
It can be, yeah. It involves tracking how small changes propagate, which means dealing with derivatives, Jacobian matrices, QR decomposition, some heavy linear algebra. But crucially, they found a way to make it practical, which we'll get to. The point is, it's mathematically grounded in the network's dynamics.
Okay, so the big idea is this reliable LS-based distance. How did they build an algorithm around it?
That leads us to LSH, LS-based Hyperpruning. There's a good diagram in figure 2. It's basically an iterative search process.
Walk me through it.
Okay, you start with a bunch of potential pruned network candidates, different hyperpruning settings. You also need that pre-trained dense reference network. Its LS is your target.
Got it. Pool of candidates, target dynamics.
Then you iterate. First phase, candidate removal.
Thinning the herd.
Exactly. You train each candidate for just a few epochs, like e-epochs. Then you compute the LS for each candidate and the dense reference. Project them into that low D LS space.
And calculate the distance to the reference for each one.
Right. Then you remove the candidates that are furthest away in LS space from the dense reference, maybe the bottom half, or ones beyond a certain distance threshold.
So you're using the LS distance as the filter, kicking out the ones whose dynamics look wrong early on.
Precisely. That's the reliable early filtering step. Then comes the candidate generation phase.
Making new candidates.
Yeah, but smartly. They adapt existing Bayesian optimization techniques, like TPE, to generate new hyperpruning configurations based on the properties of the candidates that survive the removal step.
So it learns from the survivors, the ones LS deemed promising, to explore better regions of the search space.
You got it. These new candidates get added to the pool. Usually you generate fewer than you removed, say, remove half, generate a quarter so the pool size shrinks over time.
Focusing the search, Makes sense.
You repeat this remove-generate cycle several times, you end up with just a small set of the most promising candidates identified by the LS metric.
And those ones get the full treatment.
Right. Only that final handful gets fully trained until convergence.
The expensive part, but only for the likely winners.
Exactly. Then you just pick the best performer among those fully trained models. The key, again, is swapping out unreliable early loss for this consistent LS-based distance in the crucial early selection stages.
Conceptually, that sounds really solid. Did it hold up in practice? What did the experiments show?
They really put it through its paces. Standard language modeling tasks, Penn Treebank with LSTMs and RHNs, Wikitext2 with a more complex AWD-LSTM model, compared LSH against the original dense networks and other leading pruning methods.
Okay, the moment of truth. How effective was it?
Pretty darn effective. The paper states LSH consistently outperformed dense networks and other state-of-the-art pruning methods. For example, look at Table 1, the stacked LSTM on Penn Treebank. LSH hit a perplexity of 69.9.
Lower is better.
Right. The next best pruning method they compared against, selfish RNN, got 71.7, and the original dense network was 72.4. So 69.9 is a noticeable improvement over both.
Wait, hold on. It beat the dense network. The prune version performed better than the original full-size one.
That's the kicker, the remarkable finding, as they put it. LSH didn't just match the dense performance with fewer parameters, it actually exceeded it. It found non-obvious hyperpruning settings that led to genuinely better models through sparsity.
Wow. Okay, that's huge. Using sparsity to actually improve the model, found via this LS-guided search, what about robustness? Did it work well at different sparsity levels?
Good question. Figure 3 left shows results for pruning ratios from 50% sparsity up to 80%. LSH stayed ahead of the loss-based search and selfish RNN across that whole range. So yeah, seems robust.
Nice. Better performance, robust. What about the efficiency? Did LSH actually speed up the search process?
Oh yeah, big time. Figure 3 right compares the time needed to find a good configuration. For the stacked LSTM example, LSH took about 15 hours.
Okay.
The baseline loss-based hyperparameter search took around 150 hours, over 6 days.
15 hours versus 150, that's a 10x speed up.
Exactly. A 10x improvement in finding that optimal pruned configuration. That's a massive practical win.
That really addresses the original hyperpruning search cost problem.
Definitely. They also directly compared using LS versus loss as the early criterion within various standard optimization algorithms in Table 2. And consistently, using the LS distance led to better final models, lower perplexity, for the same computational budget.
So it confirms LS is just a fundamentally better guide for this search than early loss, no matter the specific search algorithm you pair it with.
Seems that way, yes. A more effective early estimation criterion.
Okay, but let's revisit the cost of calculating the LS itself. You said it can be expensive. How did they manage that to still get a 10x overall speed up?
Right, that was crucial. They did some ablation studies and found something really practical. You don't need tons of data to get a good estimate of the LS. Table 3 shows that computing LS using just 2 validation samples gave very similar results for the key LS properties compared to using 10 samples.
Just 2 samples. That must cut down the calculation time per candidate massively.
Enormously. Down to about 12 seconds per candidate in their tests. Now, that's still a bit more overhead than just checking the loss, maybe 20% extra time per epoch during that early selection phase.
Okay, a small overhead.
But that small overhead buys you a much better filter. It lets you throw out bad candidates way more effectively, meaning you explore fewer candidates overall and waste less time on full training runs later. The net effect is that huge 10x overall speedup. The overhead becomes even less significant for bigger datasets, where each training epoch takes longer anyway.
Got it. So the cost per candidate is slightly higher, but it's so much more effective at guiding the search that the total time is drastically reduced. It all clicks.
It does. The theory, the empirical shortcut, it all comes together.
Okay, so let's wrap this deep dive up. The core problem was hyperpruning efficiently finding the best strategy to create sparse, fast RNNs using methods like dynamic sparse training.
Right, because the usual ways of searching were too slow or unreliable.
The big innovation here is using the Lyapunov Spectrum, borrowed from dynamical systems, to create a reliable, early signal, the LS-based distance, predicting which pruned networks will perform well long-term.
A signal that avoids the pitfalls of volatile early loss metrics.
And they built the LSH algorithm around this, using the LS distance to iteratively filter and generate candidates, guiding the search much more efficiently.
Making the whole process smarter and faster.
The results really back it up. LSH finds pruned networks that aren't just competitive, but often better than the original dense networks, and it finds them about 10 times faster than traditional search methods.
Yeah, the key takeaways are definitely the novel LS metric, the efficient LSH algorithm, and that strong experimental validation showing both better performance and faster search.
This feels like a really significant step for making these powerful sequence models much more practical for real-world use, especially on devices where efficiency is key. It's also just a brilliant example of cross-disciplinary thinking, right? Pulling ideas from physics and dynamical systems into AI.
Absolutely. It shows how valuable looking outside the immediate field can be.
Which kind of leads to a final thought for you, our listener, to chew on. We saw how concepts from dynamical systems, like the Lyapunov Spectrum, provided this unexpected key to unlock efficiency and performance gains in RNNs. So where else in AI might ideas from other scientific fields, maybe fields that seem totally unrelated, like thermodynamics or ecology or quantum mechanics, who knows, be hiding similar keys? What other breakthroughs might be waiting at the intersection of disciplines?
Definitely something to think about.
Thanks for joining us on this deep dive into hyperpruning and the Lyapunov spectrum. We hope this helped you quickly grasp the core ideas from this fascinating research.